Today we start about limit and cluster point. Previous day we also discussed about some topics of limit and cluster point. Now we start further. We first start from some questions. We write this question first. If A is a non-empty bounded subset of R, if A be a non-empty bounded subset, non-empty bounded subset of R, then its supremum and infimum are limit points of A. Then we have to show that its supremum and infimum are limit points of A. Okay. Now we prove this problem. Now we know about that supremum, definition of supremum. First we start, let x equal to supremum of A. Then obviously we know about that definition of supremum. Then there exists P belongs to A such that x minus epsilon less than P less than x for epsilon greater than 0, and for all A less than equal to x for all A belongs to A. Okay. This one is the definition of supremum. Now we take x minus epsilon less than P less than x plus epsilon. This implies bx epsilon intersection A not equal to 5. Okay, this implies that x be a limit point of A. Okay, then we take so supremum of A be a limit point of A. Similarly we proceed further. Then we also see that let y equal to infimum of A. Then here also definition of infimum we get for epsilon greater than 0 and there exists Q belongs to A such that x less than Q less than x plus epsilon and y less than equal to A for all A belongs to A. Okay. Then what we get? We erase this problem, first portion. Then what we get? We get simply x less than Q less than x plus epsilon less than x minus epsilon. This implies bx comma epsilon intersection A not equal to 5. This sorry, we write wrong here. Here not x, we taken y, so here y. Okay, sorry. y y, then y be a limit point of a. This implies that its infimum are limit points of a. Okay, so we done this problem. Next we further proceed. We start about this question. Let E subset of R we erase these portions now. Now we start with these questions. Let E subset of R be a non-empty bounded and closed subset closed subset. We have to show that supremum of E, infimum of E belongs to E. Okay. Now we prove these portions. Since E be closed sets, then since E subset of R be bounded and bounded, then bounded means then its supremum and infimum exist. Okay, and since E subset of R be closed, so its all limit points are in E. So in previous problem we see that supremum of E and infimum of E are limit points of E. So supremum of E and infimum of E belonging to E. That means supremum also belonging to E and infimum also belonging to E. Okay. Next we going to further. We erase this problem. And next questions. The only non-empty subset of R which is both open and closed in R is R. Questions. The only non-empty subset of R which is both open and closed in R, both open and closed in R is R. Okay, then we proceed this one. Now we construct in this way phi not is equal to a subset of R which is both open and closed, which is both open and closed in R. Then let x belongs to A. This implies that then x minus epsilon x plus epsilon subset of A for epsilon greater than 0. Okay, then let E equal to supremum of B such that x minus epsilon B subset of A. Okay, for B greater than x. Then we claim that E is non-bounded. We claim that E is not bounded. Now if beta equal to supremum of B finite, then beta belongs to A. Okay, now A be open means beta minus epsilon beta plus epsilon subset of A for epsilon greater than 0. Okay, now since beta minus epsilon is not an upper bound of E, since beta minus epsilon is not an upper bound of E, then there exists beta belongs to E, V belongs to E such that beta minus epsilon less than V. Okay, but x beta plus epsilon equal to x beta union beta minus epsilon beta plus epsilon subset of A. Then this shows that beta plus epsilon belongs to E. So a contradiction to the fact. Okay, a contradiction to the fact beta equal to supremum of E, because beta plus epsilon also belonging to E. So what we get x plus infinity subset of A. Okay, so what we get x plus infinity subset of A. x plus infinity subset of A. Okay, now we erase these things, this portion. Now we get further. We take similar procedure for beta equal to infimum of E, or alpha equal to, if we take alpha equal to infimum of E, then also minus infinity x subset of E, subset of E. Okay, then we get then A B not bounded, so A equal to R, which is both open and closed. Okay, now we're going to further. We also discuss another problem. Let E be a subset of matrix space with the following property. Let E be a subset with the following property. If a sequence xn in X converging to a point X belongs to E, then there exists n belongs to n such that xn belongs to E. For all n greater than equal to n. Okay. Now we have to show that E be open. Okay, so simply discuss about this problem. E be open means that is X reference E be closed. Okay, X reference E be closed means all limit points of, that is all limit points of X difference E are in X difference E. Okay, now let X be a limit point of, let X be a limit point of x difference. Then we have to show that x belongs to x difference. Now if x belongs to E, then we get xn such that xn belongs to E and Vx xn such that xn belongs to E and xn converges to xn converges to x. Okay. Now V, since x be a limit point, then xn converges to x E. So xn belongs to E. So we find a delta. Greater than 0 such that Vx delta intersection x difference E equal to 5. Okay. So x be not a limit point of, if x belongs to E, then this one equal to 5. Okay. So x difference E be not contain, so x be not limit point of, so x be not a limit point of x difference E. Okay, because we choose any a delta such that this one Vx delta intersection x difference E is equal to 5. Then x be not a limit point of x difference E, hence so this one is a contradiction because x be a limit point of E, so obviously x does not belongs to E. This implies x belongs to x difference. This implies x difference E be closed. Okay. Hence E be open. Now we proceed further. We erase this portion. We are going to further proceed questions. These questions are: the diagonal is closed in the product matrix space. Is closed in the product matrix space. Okay. X Cartesian product X. So how we proceed? We proceed to different way. Okay. First, we just see about that. We take D equal to x such that x belongs to x. Okay. Then let PQ belonging to x Cartesian product x be a limit point of D. Be a limit point of D. Then P delta P plus delta Cartesian product Q difference delta Q plus delta intersection D, okay, not equal to 5. PQ be a limit point, so this one is possible. This implies that for epsilon greater than 0, P be so small that P difference this one equal to Q difference this one and or approximate to, okay, approximate to and P plus delta approximate to Q plus delta, then this one be possible, okay, otherwise this one can't be possible. So P equal to Q, then P belongs to D and D be closed. Okay, in this way we do this problem, and another way we also logically develop. How? This one also too easy. This one we start, let xy be a limit point, xy be a limit point of the diagonal converges to xy, limit point, okay, then limit point, then also xn converge to x and yn converge to y, okay, but uniqueness of the limit x equal to y, okay, here sorry, xn and xn converging to y, okay, because this one is the diagonal element, since xn belongs to this D diagonal element. So by uniqueness of limit x equal to y, hence all limit points of diagonal lie in the diagonal. Hence all limit points of the diagonal are lie on the diagonal. So the diagonal is closed in the product matrix space. So the diagonal Okay, so today we stop here.